Hello and welcome to the equation of states for an ideal gas session. The reason we see the one ring to rule them all in front of you on the screen is because this equation of states brings together all of the gas laws to create one law which rules an ideal gas, at least. I'll explain about ideal gases in a later session. Let's just say this is a way to describe gases as a whole. So previously, when I was talking about pressure, I mentioned Boyle's law. Boyle's law states that the absolute pressure of a fixed mass of an ideal gas at a constant temperature is inversely proportional to its volume. So P times V equals a constant. That is not the only gas law. Some other ones which I haven't mentioned, but I'll mention now. If we look at Charles's law, and this is the relationship between volume and temperature at constant pressure. So if we had a syringe, for example, at atmospheric pressure, and we had an initial volume and initial temperature, if I increase the temperature, so the volume would also increase. And that is described as Charles's law, that a volume of a fixed mass of an ideal gas at a constant pressure is directly proportional to its absolute temperature. And in turn, we see that volume divided by temperature equals a constant, assuming pressure has been maintained constant. We've also got Gay-Lussac's law, which is the relationship between pressure and temperature at constant volume. So if we have a container which has a fixed volume, and what we can do is if we increase the temperature, then what will happen is the pressure will increase. And this law states the absolute pressure of a fixed mass of an ideal gas at a constant volume is directly proportional to its absolute temperature. So pressure divided by temperature equals a constant volume. Now let's bring all these gas laws together. If we bring these gas laws together, we can combine into a more useful law. Okay. So we accept that pressure times volume is proportional to temperature. If we can incorporate mass of the gas, which also should be taken into account, our relationship becomes pressure times volume is proportional times mass times temperature. Now, this proportional relationship can be made into an equation by adding a constant. Now, this constant would be different for different gases. However, if instead of using the mass, we use the number of moles of gas, that allows us to have a greater alignment. So what we can have here is pressure times volume equals the number of moles multiplied by a constant R times T. This constant R is known as the universal gas constant and has a number of 8.31 joules per Kelvin per mole. Okay, this is the equation of state of an ideal gas, and it allows us to explore pressure, volume and temperature changes of a gas, and allows us to make some measurements and make some predictions about that. Let's think of some examples. So another way of doing this is to say that pressure times volume divided by temperature equals nR, the number of moles times by a constant, the universal gas constant. This means that pressure 1, volume 1 divided by temperature 1 is also going to be equal to pressure 2, volume 2, temperature 2. This is a great way of working out if we have some knowledge about how one of these factors will change due to the pressures and influences and temperatures of the others. Now, it's not quite as simple as this, because real gases reach a liquefaction point or boiling point at some temperature above absolute zero, so the graph can't be extended below this point. For that reason, this is for an ideal gas. An ideal gas is a model gas which doesn't have this issue, and thankfully it fits the idea of a real gas across a very, very wide range of temperatures. So therefore, as we're saying, everyday temperatures and pressures, the equation is close enough to perfect and we don't need to worry about that. But we use the term ideal gas just to distinguish between real gases, because the law breaks down at those extreme temperatures and also extreme pressures. So let's cover a couple of examples here. Example number 1, calculate the volume of 1 mole of an ideal gas at STP. So this is standard temperature and pressure. Standard temperature is 273 degrees Kelvin and pressure is 1 atmosphere. So I'll give you a moment to think about that. Pause. Your answer should look a little bit like this. 1 atmosphere, it needs to be converted into pascals. PV equals nRT. Volume is what we're looking for. So we know what the N is, the number of mole. We know what the constant is for R. We know the temperature in Kelvin is 273. And we know the pressure in pascals is 1.013 times 10 to the 5, which gives me 22.4 times 10 to the minus 3 meters cubed, or 22.4 litres. And you'll remember a couple of sessions ago I made a statement, I think this is when I was talking about molar mass, is that 1 mole of gas is always 22.4 litres, and this is the reason why. Okay, another example. Example 2. A mass of gas has a volume of 20 litres at 17 degrees Celsius and a pressure of 1.8 times 10 to the 5 pascals. What will the volume of the gas be if the temperature is raised to 357 degrees centigrade and the pressure is lowered to 1.2 times 10 to the 5 pascals? Again, pause, take a moment to try and do this calculation. Remember, think about temperature in Kelvin. That's my one big hint. Solution 2. Here, what we need to think about is by rearranging for V2, everything else is known. So we've got pressure 1, volume 1 times temperature 2 divided by pressure 2 divided by temperature 1. And that gives us a volume of 65.2 litres. Now, this is the one rule which rules them all, because in any situation, if we have a constant, we can always work back to the original gas laws. So this is the bringing together of all the laws and allows us to work out these situations. One final note here is something about Boltzmann's constant. The ideal gas equation can be rewritten in terms of the total number of molecules present instead of the number of moles. To do this, what we have to do is remember that the number of molecules, N, is equal to the total number of molecules per mole times the number of moles. So this is Avogadro's number multiplied by the number of moles. If we put this into the equation, what we find is PV equals nRT. So N can be shown as the number of molecules divided by Avogadro's constant, and then what happens is the universal gas constant divided by Avogadro's constant gives us a value known as K, and that's known as Boltzmann's constant, and it's just the gas constant divided by Avogadro's constant.